In this video, we're going to see PN junction solar cell. In fact, this is in continuation to the previous video where we have discussed photodiode. If you haven't seen that video, please do make a point to see that video before this video. Here I have taken the diode circuit symbol where I am showing incident light and the current characteristics of a normal diode, and when light is incident, these are the current voltage characteristics of the diode. Now we have seen from the previous video that when we operate in this region, we said it is going to be like a solar cell where it's going to generate electric energy from the incident light. But in order to take the full benefit or harness the characteristics in this region, we cannot use a normal diode. The diode should be manufactured in a specific way to enhance and use the characteristics in this region. So that's why the PN junction solar cell is manufactured in a very specific way. I'm going to take that structure here. This is how the structure would be of a PN junction solar cell, in which we can see here this is N-type material, this is P-type material, hence this is the junction between them. And we have a metal contact here which we call back contact. And if we come to this region, we have this black regions which we call metal contacts. In fact, it is all only a single metal, but they're done in finger fashion. When we incident light from this side, the light could actually hit this metal and which doesn't go into the PN junction. Hence, that region is not really useful. Hence, that's why we don't make a continuous metal contact here. Instead, we make this like in finger kind of fashion. We can see this better in three-dimension picture. We'll see it later. Now, when the light actually comes in these regions where the light can actually get reflected back, hence, in order to accommodate the light to go in, we have an anti-reflection coating so that whatever is incident, majority of it actually goes into the PN junction. Now, the intention of making N region very thin is because if the photons actually come into N region and excite and create electron hole pairs, they wouldn't be separated and transportation wouldn't be accommodated because there is no electric field in the N region. We want these photons to effectively create electron hole pairs in the depletion region where electric field is present, which would separate them and accommodate the transport of them, where we would see the effect of current because of this incident light. That's the reason why we made this N region very thin. Assuming most of the photons are absorbed in the depletion region, very small would go into the P region, where even they wouldn't be of much importance because this is neutral region where there is no electric field. This is the three-dimensional model in which we can see the finger structure for the metal contact made on the N side. Now, coming back to the current voltage characteristics, we have seen that this is the short circuit current and this is the open circuit voltage. In order to find these values in terms of formulas, we're going to find the equivalent circuit for this PN junction solar cell. To do that, let me take the energy band diagram in which electric field is present in the depletion region where electron hole pairs are generated due to the incident light, and this electric field would send the holes to the P side and electrons to the N side. This is the current because of the incident light. This current we said is IL, which is in this direction, which means IL always will be from N side to P side because the electric field in the depletion region is always from N side to P side. Now, trying to draw an equivalent circuit for the PN junction solar cell. So, let me take the diode where we have light incident on the diode, and let's say we have some current flowing here and potential across the diode is, let's say, VD. And this is ID. Now, how do we represent this in terms of a simple normal PN junction diode and something extra? So, what we can say by understanding from here is there is a current component which is extra because of the incident light, which was not present in a normal PN junction diode. So this current component I'm going to take as a current source here, which is in the direction N side to P side. So I'm going to put the direction this way, N side to P side. But the PN junction diode is in this way. I'm going to put a normal PN junction diode here, not this solar cell under incident light. So I'm going to take a PN junction diode here, whose current characteristics would be I naught times e power Vd over Vt minus 1, assuming that the potential here is Vd and the current that is flowing here is Id. This current is IL. Now the key point is, because of the incident light, there is some current that is flowing, which we called IL, which is shown here as a current source, which tells us the dependence of current because of incident light here. But in this case, we are not showing incident light. And the actual diode behavior, which is present even when the incident light is present, that is shown with this normal diode, which has this current to voltage relationship given by this equation. So this diode can be equated to this, where we are not showing incident light, but its effect is actually captured by this current source. Now taking this as a starting point, now let's find out the equations for the short circuit current and open circuit voltage. Let me move to a new page. Here from this equivalent diagram, we can say ID is equal to I naught times e power Vd over Vt minus 1. That's a current flowing through this diode, which is given by this equation, minus IL. This is the current that would be flowing through this diode under incident light. So now looking at what is open circuit voltage. Open circuit voltage, VOC, is nothing but Vd at which Id is equal to 0. So now as we have this equation, let's make Id is equal to 0. When we make Id equal to 0, we have to substitute that Vd is equal to VOC. So let's do that. So 0, Id is 0, equal to I naught times e power VOC over Vt minus 1 minus IL. This can be written as IL over I naught plus 1 is equal to e power VOC over Vt. We can write this again equal to VOC is equal to Vt ln of IL over I naught plus 1. This is a very important expression. By knowing the thermal voltage IL and I naught, we can figure out or find what is open circuit voltage of the PN junction solar cell. Now coming to the second point, ISC. What is ISC? ISC is ID at Vd is equal to 0. So let's substitute Vd is equal to 0 in this equation. Then Id is equal to I naught times e power 0, which is 1, minus 1, e power 0 is 1, minus 1, minus IL. So as this is 1 minus 1 is 0, so this term goes away. So we have ID is equal to minus IL, which is ISC. So we can say that the short circuit current is nothing but the IL in magnitude. So let me put this here, ISC is equal to minus IL. Now let's look at this current voltage characteristics under the incident light, as we are interested in the fourth quadrant. To make it simple, let's flip the characteristics in the fourth quadrant above and redraw it here. Here I have taken the fourth quadrant current voltage characteristics flipped and shown as if it is in first quadrant for simplicity, where this is voltage axis and this is current axis. Of course the current is negative. ISC and VOC is shown here. Now these are like the extreme cases. That's the maximum current that we can see and the maximum voltage that we can see. Of course not at the same operating point. But ideally, if you see, the maximum current that we can see is ISC, and the maximum voltage we can see is VOC, but of course not at the same operating point. But this product is the maximum. But in reality, we would operate at some point, either here or somewhere. So let me pick some point here, where the product of voltage times current would be nothing but the area under this curve, which is the product, the current value times the voltage value. Now if we move somewhere here, the voltage would be some point here and the current would be some point here. So in this case, the area is higher, which means the product here, I times V, is higher than the product I times V here. Now if we move here, again the area would be smaller. So which means as we move from this point to this point, or this point to this point, there is some point somewhere between, at which operating point the power is highest. So let's call that the power maximum, at which point we would say this is Vm times Im. So let me say that is this point. So let me call this Pm. This will be the area of that rectangle. Now ISC times VOC would make a rectangle like this. This product would be VOC times ISC. Now the ratio of the maximum power, that is Vm Im, to that of VOC ISC is called fill factor. You can think of this quantity as if how much portion of this rectangle is actually filled with this one. So in fact, obviously this rectangle area will be always less than this rectangle area, which means this quantity is going to be always less than 1. So this is a very important expression or definition. Now coming to the next important point, that is conversion efficiency. In short form, we can say efficiency. We have a symbol for this, eta. Now this is defined as the maximum power delivered by the solar cell. Let's say that is Vm times Im over the input power. The input power is nothing but the incident light power. So let me call that Pin. So we can rewrite this, as we know Vm Im is related to fill factor to VOC ISC. So we can say fill factor times VOC ISC over the input power. We are writing it in terms of this because most of the cases we know what is VOC and ISC, and in fact in data sheets we would know what is fill factor. So, or in case in problems we are given only these values, we substitute and get these values.